Hey everybody, I'm just getting ready. We're going to be starting a little bit early today. Sorry, like I said, about missing the stream yesterday or yesterday, one of those days. You know. Okay, so got the chat out to say hi to everybody. So let's just start the stream. All right, so welcome everybody to Keenan Can Do, where we just figure out some stuff, play around with Emacs, play around with some. We're currently learning C Programming using Emacs. So today we'll continue on with the Beja's guide here, section 12, memory allocation. And then later on, we're going to play with some of the Emacs stuff. I'm going to actually look at the Prelude Emacs Kickstarter. I think that's got a lot of cool features in it that could get people started pretty quickly with Emacs without a lot of effort on their side. So let's start with that. We'll turn on some background music for you here. Let me know in the chat if that is too loud or not, and I'll adjust it as needed. Let me set my chat on there, and we'll go off of studio mode. Okay, so if we look at let me turn it down just a little bit. If we look at where we were, we did the allocation example here using the malloc. So we're going to move on to 12.5.1 here, reading in lines of arbitrary length. Says I want to demonstrate two things with this full-blown example. Use of realloc to grow a buffer as you read in more data. Use of realloc to shrink the buffer down to the perfect size after we've completed the read. What we will see here is a loop that calls fgetchar over and over to append to a buffer until we see that the last character is a new line. Once it finds the new line, it shrinks the buffer to just the right size and returns it. Alright, that sounds interesting. So let's go ahead and create a new file. I guess we could do it in memalloc, but we're going to call it realloc. So let me ask to cancel there. We'll go into dirred buffer. We'll go up here and let's make a new folder. We'll call it the realloc folder. And then in here, we'll go ahead and find our main.c. All right, so we do have the information in here now to begin. So let's get in our stuff that we'll need, our standard input.ih. Let's get in our standard lib. Is it where that's at? Yes, it is standard lib for realloc. And then we'll start with a voided main function, just like our normal day-to-day C stuff. And we'll do the obligatory hello world. And I'm not going to forget the new line character this time. I don't need anything in there. So that should be good. So let's also give ourselves a make file here, and we'll say that we have some C flags. We do want extra errors. We do want our standard to be C89. For right now, we might look at the later standards at a later time, but for right now it's C89. We do want G for the debug symbols, and we do want to be pedantic, right? So then our target main just requires main.c, and it simply calls cc with the C flags, and outputs, call cc with the C flags from main, giving in main.c. Believe that's what we need. Boom, boom, boom. Let's go ahead and save it. Let's go ahead and go back here, and then we'll compile it. Should just be make. Can't find main. Yeah, so that means that we do want the minus O, like that, right? And then we'll go back to our C file, and then let's compile it one more time. There we go. So then if we go over to our terminal here on the bottom, pretty much by my face right there, we're going to CD down and go into that realloc, and then we'll operate main, and we should see a hello world. So we're good to begin. I like doing this every time to get into that that habit of, I mean, it's boilerplate for right now, and once AI is in the field, do all that, but to get into the habit of making sure I understand, and you're setting up your project to a good set. So what we're gonna do is start off with an offset of 0, index the next char, goes in the buffer. Okay, that makes sense. And then our buff size is beginning with 4. That's okay. Char star for buff. We don't know what we want that size to be yet. And then int c, the character we've read in. Okay, makes sense. And then buff is just going to be a malloc of buff size, so 4 bytes. So that would give us 4 chars initially to read in. Let's go back over here, and then we're seeing that if the buff equals null, that's an error check. So if it's null, we want to return null. Wouldn't we just return -1? I don't know if I can return null. We'll see if that even compiles. Let's see if that compiles. A buff is undeclared first use in the function. Did you mean buff size? Bum 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 bum. No, I said buff equals malloc. Error. Buff size undeclared first use. Did you mean buff size? Buff. Oh. Yeah, I did mean buff size. So we'll go to that error. Let's delete that. Oop, wrong thing. I forgot that we have that. Wrong. The code's not doing the deletion until we go. I guess we have to go forward, and then we can do the delete because of that stuff. That's one thing I think when we look at the returning void from a function, it makes integer from pointer without a. Yeah, I don't want to return void. Did it say void for this function? Oh, the function is char readline. Ah, so this is a new function. Yeah, I should have seen that. Okay. So let's go ahead and grab all of this stuff here, and we'll cut it out of here, and then we'll start with that new function, which returns a pointer. It takes in a file pointer. And then we'll put all that stuff back in there. Now we have that, and now we should be able to recompile. Yeah, no errors then. Okay, so we'll continue on after we have that error check there. Then we're saying that's the main loop. So while c equals the fgetC, right? Passing in the file pointer. C is not equal to the new line, and C is not equal to end of file. If all 3 of those things are correct, then we're going to check if offset equals the buff size. Buff size -1. If it is, 2 times the size equals 2. Right, and then I'm guessing we're going to get a new char star new buff using that realloc. Realloc buff to the buff size, the new buff size. And then we do another just error check there. If new buff equals null, then there's an issue. We didn't get our reallocation. We'll free buff on error, free, and bail. Okay, and then we'll return null, right? Otherwise, buff will be new buff, right? Yep, that makes sense. And then we'll be out of the while loop at that point, or we'll be out of the if, I guess. Yep, and then, so that buff item for offset, and then post decrement it, or so post increment it equals the character at C, the char, and then we'll close the while loop. And then we hit a new line, so that means we hit a new line or end of file. If at end of file and read no bytes, free the buffer and return null to indicate we're at end of file. Okay. So if C, so if we're at the end of file and the offset is equal to 0, then free the buff and return null. Shrink to fit. If offset, okay, this is where we're doing the shrinking. Buff size -1. If we're short of the end, char new buff equals realloc buff offset +1 because of the null terminator. Yep, that makes sense. If the new buff, again, we're doing that protection. I think we would just use that as a function at this point. If new buff is not equal to null, then buff equals new buff. And then we'll close out that for, and we'll close out that one. And then buff offset equals the null terminator, because now we want to terminate the null value, and then we'll return the buffer. Okay, so that means then that we could use it in the, okay, we don't need this anymore, so we'll do a file pointer that we're going to use to pass equals f open foo.text, which we doesn't have yet. So we'll create foo.text in a little bit. Char star line while line equals read line fp is not equal to null. Print f s sent in line free line, and then close. Of course, we're going to close the file pointer. Okay, before we try it out, let's read up to this, read up to where we're at here. No. When growing memory like this, it's common, though hardly a law, to double the space needed each step just to minimize the number of reallocations that occur. That makes sense. Finally, you might note that readLine returns a pointer to a malloc buffer. As such, it's up to the caller explicitly to free that memory when it's done with it. Which is what we did on line, whatever line that is, line 68. Finally, you notice that, yeah. Yep. Okay, so let's try that out. Let's see if I have anything in foo.text. But no, there's no foo.text, so let's just Echo some stuff to foo.text, and echo some more stuff to foo.text. Oh, echo some more stuff to foo.text, and then echo hello some more stuff with words to foo.text as well, and then cat foo.text. Oh, it's just that. So you overwrite it each time. That's fine, because that's the line. Sure, we'll go back here in Emacs, and then I guess I can add some more information to it. Here is a second line, not spelled right. Here is a third line, but spelled right. Spelling's hard. Oh man, save this. Go back to that buffer. Should we compile it? Let's try to compile it, folks. Error, undeclared. Of course it is. New buff. First use. Did we not do new buff? Oh, because I'm spelling it with a F at the end, and they're not, so... man. No, I didn't want that. New buff. New buff here as well. Spelled wrong here as well. Okay. So recompile. Now it finished. Okay, so let's run it. Let's run it and see what we get. Here are some stuff with words. Here's the second line. Here's the third line. That's pretty cool. That is really, really cool. Okay. So what did we learn? Let's see what we learned. Let's step through the code and look at what we learned with this function here. So it's our own kind of implementation of a read line. We're setting an offset. Buffer size equals 4. We're allocating it to the initial. And we have a check at this point. At this point, buffer better have something, right? So that's what that does. Okay. And then this is our main loop. So we're using the while. We're getting the, okay, so in the while loop here, in this while we have initialization, or I'm sorry, assignment and a check. That's the first time I saw that. All right. With assigning and checking at the same time in that while loop. So that's interesting. Because we could just do, right, we could have just taken that out. Oops. Ah. What is this? Take a screenshot. What? What happens when you press too many Emacs keys there? Is my number lock not working? Let's see. Oh. I thought the replay buffer. Hold on 1 second. Hold on, because my replay buffer is supposed to do. Where's my settings? 1 second here. That happened again. That always happens. I'm always doing that stuff. Give me 1 second, guys. I need to look at this replay buffer. I'm trying to get this replay buffer to work the right way. It started it. The hotkeys for it is that. But that didn't work. So let me do, let's do control, super R, apply. Okay, so now if I do, how do I know if it saved a replay? Let's go look at the files. Recordings? No. No, there's nothing there. One moment, one more time. Stream, output, recordings, replay buffer, recordings go to home caddy code. So it just goes to the main, it just goes to here. So I should see. So do I have to go here and do it? Yes, there it is. Oh, okay. So if I'm gonna do it, I have to be back into OBS. So OBS doesn't. Oh, I want the hotkeys. Let's see. Isn't there a setting that says don't overwrite the hotkeys? Never disable hotkeys. Yeah. So if I'm back in here in Emacs, it should still grab it. No, it doesn't grab it because Emacs is grabbing everything. Okay, so I'll have to flip over really quick, do like that, and then it'll create the replay buffer. So I just need to remember that. That's fine. Doesn't really bother me too much. Okay, let's get back into what we're actually doing, the actual coding at hand here, folks. Let's get back into the actual coding at hand, which is what we want to do, which is what we like to do, and that's what we're going to do. Okay? All right, so realloc with null. Trivia time. These two lines are equivalent. Char pointer malloc 3490 and char pointer realloc null to 3490. That could be convenient if you have some kind of allocation loop and you don't want to special case the first malloc. Oh, that is cool. Okay, very interesting. That could be convenient if you have some kind of allocation loop and you don't want to special case the first malloc. So for instance, in the example, null pointer, or I'm sorry, integer pointer, null into null. Why are we using null so much? Is null even, did we have the null keyword in C89 keywords? Did we have the null key? We did have the null keyword in C89? Bum, 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 la, la, la. La, 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 la. No, what? Is null part of standard lib? Yes, it is, isn't it? So if we do find grep and no, it's not that file, not that folder. Let's go to, we want to grep, not there. I want to grep to, no. Is it USR includes? Include, yeah. Okay, and then dirid grep, dirid do find flag file. Grep dirid, is it grep dirid? Grep, find grep dirid, yeah. Okay, and we want to find the define null. Find finished. So I did it wrong. we want to find, is it just defined like that? Maybe. There it is. So what? So it's in this. Includes C. This is standard C. You should include this file in your program more than any H. Rather than, this is the C version header, and its contents are mostly the same as that, but are all contained in the namespace except. So then why? Then where's C? Where's C? C. Standard lib. Boom, boom, boom. Where's standard lib? Are we looking for the standard lib? There it is. So is this not where it is? Oops. Get size and null from standard def. Yeah, so standard def. So standard def. So how come it didn't? Where is standard def? Define include standard def.h. Where? I see standard bit. Standard def. Of course, it's gonna be a lot. Oh man. That's the only one? Whoops. So where are the standard libraries for? Is it Linux? No. It is in Linux. Okay. So where's null? Oh, we don't have null. So where's null then? Huh. So those aren't there either. Okay, I'm going on a yeah, I understand this. Okay, I'm going on a tangent. Obviously, it probably comes from standard lib, so that's where it's from. Okay. So, yep. Int star p equals null. Int length equals 0. While not equal to done. Allocate 10 more. Ints length plus equals 10. P realloc. Size of star p times the length, do amazing things. In that example, we didn't need an initial malloc since p was null to start, so we just did the realloc from the beginning. Aligned allocations. You probably aren't going to need to use this, and I don't want to get too far off in the weeds talking about it right now. But there's this thing called memory alignment, which has to do with the memory address pointer value being a multiple of a certain number. Yep. For example, a system might require that a 16-bit values begin on memory addresses that are multiples of 2, or that 64-bit values begin on memory addresses that are multiples of 2, 4, or 8, for example. It depends on the CPU. Some systems require this kind of alignment for fast memory access, or some even for memory access at all. Now, if you use malloc, calloc, or realloc, C will give you a chunk of memory that's well aligned, or any value at all. Even structs works in all cases. Oh, sorry, I read that wrong. C will give you a chunk of memory that's well aligned for any value at all. Even structs works in all. This works in all cases. But there might be times that you know that some data can be aligned at a smaller boundary or must be aligned at a larger one for some reason. I imagine this is more common with embedded systems programming. In those cases, you could specify an alignment with aligned alloc. The alignment is an integer power of 2 greater than 0. So 2, 4, 6, 8, 16. And you give that to aligned alloc before the number of bytes you're interested in. I imagine this is more common with embedded. Okay. The other restriction is that the number of bytes you allocate needs to be a multiple of the alignment, but this might be changing. See defect report 460. Let's do an example allocating on a 64-byte boundary. No, I don't really need to do that. I wanted to throw a note here about realloc and aligned. Realloc doesn't have any alignment guarantees, so if you need to get some aligned reallocated space, you'll have to do it the hard way with memcopy. Here's a non-standard aligned realloc function if you need it. Void aligned realloc, pointer, void pointer, old size, alignment size. Okay. Note that it always copies data. Okay, so that's the end of chapter 12. So where are we at now? To scope. To scope. Scope is all about what variables are visible in what context. Yeah, so I could probably speed through this pretty quickly because I'm sure all of the other C-like languages that I've been programming in for a long time borrowed their scope rules from C, in which C probably borrowed some from like the lexical languages like Lisp and stuff like that. So we'll see what kind of scope applies. This is the scope of almost all of the variables devs define. It includes what other languages might call function scope, i.e. variables that are declared inside the function. The basic rule is that if you've declared a variable in a block delimited by squarely braces, the scope of that variable is that block. If there's a block inside a block, then variables declared in the inner block are local to that block, cannot be seen in the outer scope. Once a variable scope ends, that variable can no longer be referenced, and you can consider its value to be gone into the great bit bucket in the sky. An example with nested scope. Local to outer. Yeah. Where to define variables. Another fun fact is that you can define variables anywhere in the block within reason. They have the scope of that block, but cannot be used before they are defined. Okay, illegal, can't use J. Historically, C required all variables be defined before any code in the block, but this is no longer in the case in the C99 standard. Yeah, so that's, if you notice, that's what I do. Coding has become like an ancient thing so fast. Okay. I don't know what that means. Historically, C required all the variables to be defined before any code in the block, but this is no longer the case in the C99 standard. Yeah, so if you see, I'm actually using C89 just because I want to get back to the beginning. I want to be ancient, as that viewer so eloquently put it. Ancient over here. We're ancient. Variable hiding. If you have a variable named the same thing at the inner scope as one at the outer scope, the one at the inner scope takes precedence as long as you're running in the inner scope. That is, it hides the one at the outer scope for the duration of its lifetime. And we call that shadowing in other languages like Python. You shadow something. That's duck typing though, so maybe it's different because it's not strongly typed. You might have noticed in that example that I just threw a block in there at line 7. Not so much as a for or if statement to kick it off. This is perfectly legal. Sometimes a dev will want to group a bunch of local variables together for a quick computation, and we'll do this, but it's rare to see. Inner scope, yep. Outer eye is hidden. Okay, so you can just quickly throw a block in there, do some local computation to that block, and then jump back out. Cool, makes sense to me. File scope. If you define a variable outside of a block, that variable has file scope. It's visible in all functions in the file that come after it and shared between them. An exception is if a block defines a variable of the same name. It would hide the one at file scope. This is closest to what you would consider to be quote-unquote global scope in another language. For example, if I declared and assigned int shared equals 10, file scope visible to the whole file after this. Function 1 shared plus or equal now holds 110. Function 2 print shared prints 110. Int main call both functions. Yeah, that makes sense. Coding has become that's a bot. This person ABDCEFGHWPX1. So that's literally the name. That's definitely a bot. Note that if shared were declared at the bottom of the file, it wouldn't compile. It has to be declared before any functions use it. There are ways to further modify items at file scope, namely with static and extern, but we'll talk about those later. For loop scope. I really don't know what to call this, as C11 doesn't give it a proper name. We've done it already a few times in this guide as well. It's when you declare a variable inside the first clause of a for loop. In that example, i's lifetime begins the moment it's defined and continues for the duration of the loop. I would say it's like lexical. So it's for defines a block actually. For is just come on, Beach, you know, for, so what we have there, so let's say we just opened up another test.c, and sure, test.c, and int main void, right, we just have this in there, return 0, just for something, and you have in there, hi, Anoobhab, how are you? You have in there a for loop, right? Like they're saying, int equals 0, I is less than 5, I plus plus, right? Printf, let's say we're just gonna print out the value of I, and then a new line, right? And then I, obviously we don't have printf in there until we include it. So we're gonna include that to have that in there. Right, we're gonna print that out, and right, so we can compile that now, right? We can compile that and say gcc what is this, test.c to test, right? Save the file, error, undeclared identifier before token, int 0 equals 0. Yeah, I need to have I there, right? Yeah. So that was my fault. That's my fault. We're gonna recompile, save it again. So cannot find test. Why? Oh, because I didn't save it. So compile here. GCC -o test.c. Okay. So then if we go in there, I don't know, right, it just does all of the numbers. But this for is just syntactic sugar for saying I have a int out here, I, or just say j, or like, you know, I'm just gonna comment this out for right now so it doesn't even mess up anything. I have an int out here, I, and I could say while I is equal to 0 and I is less than 5, right? Then I could say printf, and then the n, again, new line, the I, and then I could just increment the I there, or I could have even just incremented the I instead of in here, right? So I don't even need this line, just using a post increment. And the I is local to, it's for this scope, the scope of the main variable, but it's kind of like enclosed in the for loop for while when it's running. So let me recompile here. Expected a before, did a before? Expected a before with the before? With where? I equals 0, I is less than 5. Oh yeah, I guess I'll bring it out. Gonna recompile. Yes. Yes, I am learning C. And also like just messing around with Emacs and things like that, so I don't get to use those languages in my day-to-day. So yeah, save file. Wow, why's my while messed up? Oh, because you don't need a freaking semicolon in there. Oh man. Wow. But okay, so as I was saying though, it's just syntactic sugar. The for loop is just syntactic sugar for I'm sorry. The for loop is just syntactic sugar for the while loop. It just kind of wraps it doesn't exist, essentially. The compiler creates the while, it turns the while loop into a for loop. I'm sorry, turns the for loop into a while loop, I believe, during the turning it into the machine code, I believe. I mean, we could go into Windows and look at the deassembly of that, but I'm pretty sure that's what it is. I think that the while is actually what the looping structure happens. Do I have exposure to programming earlier? Yes, I've been a developer for 10 years. Yep, but higher level languages, like object-oriented languages, not anything with where I had to do manual memory allocation. So that's really why I'm diving into the C, as for like the lower level stuff. But I've been for a while. How about you? Sorry, the chat is a bit off. I don't get your chats immediately when you send them, so I'll be sure to look over there every once in a while. What I've actually done in the past, and I could do it here, is put the chats on the screen. It just, depending on where I put it, it could get in the way of what's going on with the other stuff. But we'll do it. Let's do it today. We'll do it because we're having fun. We're having fun and fun stuff. We must continue to have fun. So let me create a browser source quickly here. I'll name it chat, and I'll put the YouTube in there. And I need to now go. There is a YouTube chat overlay in GitHub. Yeah, here it is. Boom, boom. So I just need to grab this CSS here, this style, and edit the chat here. So there's that custom CSS, and then I can put the chat over here a little bit. So it doesn't get too much in the way of the thing. And then is it showing then for every, does it see, do you see the chat now? Should see the chat now. You should see the chat now, so it should be updating. Let me know if it gets in the way though of everything. Hopefully it's not. Okay, so back to where we were doing. I was just saying I'm not sure. It says it doesn't know why it's called that, and I'm thinking that it's still block scope. Syntactically, it just gives the lifetime of it within that loop for some reason. Illegal I is only in scope for the for loop. Oh, so it is only in scope for the for loop. So it's not like the while. So that's interesting. So I wonder if it destroys it somehow or something. Huh. Interesting. Unless, of course, that inner scope hides them. This crazy example prints 99 5 times. For I, int I equals 99, hide the I in the for, print I. Yeah, so it hits the 99. No, and note on function scope. The C spec does not refer to function scope, but it's used exclusively with labels, something we haven't discussed yet. More on that another day. Okay, so that was 13. Now we could go to 14. Types, way more types. So the contents, the sections of this are signed and unsigned integers, character types, more integer types, how many decimal digits, converting to decimal and back, constant numeric types, integer constants. Interesting, okay. So I think for that, I don't know if I want to look at the types quite yet. Those types that they're talking about. I don't know if I want to look at them quite yet. What do you think, chat? Do you think I should look at them? Let me see if there's even anybody in chat. No, there's zero. I don't think anyone's watching. I am all by myself. Okay. So I think what I want to do is spend, let's just spend like, yeah, because all the types and stuff, I don't really kind of care about those right now. Conversion, string to numeric values, char, numeric, integer, implicit, qualifiers and specifiers, the last arg, the alternate char argv, fun facts, the C preprocessor. Actually, I do want to go through those because I do want to get to the point where I'm making that thing soon. And just as a side note, you guys should all subscribe to this channel if you like this old man over here trying to program. So if you look at my channel, I have 96. Oh, 96. We went up today. We're going for 100. When we hit 100 subscribers, I'm gonna do a special jig or something like that. Maybe I'll program a cool like 100 subscriber flash screen and in one of the languages that I'm an expert, more of an expert at. Otherwise, I'll get to the point where I can use the Raylib library or something like that and see and do it with that. So please subscribe to follow more, and we'll continue on with that. Okay, so yeah, let's start with the types. I'll just go through it quickly. We're used to char, int, and float, but it's now time to take that stuff to the next level and see what else we have out there in the types department. Signed and unsigned integers. So far we've used int as a signed type, that is a value that can be either negative or positive, but C also has specific unsigned integer types that can only hold positive numbers. These types are prefaced by the keyword unsigned. Int A, signed signed, unsigned, unsigned. Why? Why would you decide you only want to hold positive numbers? Answer, you can get larger numbers in an unsigned variable than you can in a signed one. But why is that? You can think of integers being represented by a certain number of bits. On my computer, an int is represented by 64 bits, and each permutation of bits that are either 1 or 0 represents a number. We can decide how to divvy up these numbers. With signed numbers, we use roughly half of the permutations represent negative numbers, and the other half to represent positive numbers. With unsigned, we use all of the permutations to represent positive numbers. On my computer of 64 bits, int s uses 2's complement to represent unsigned numbers. I have the following limits on integer range. Int, -9. Whatever that is, unsigned int. Okay, notice that the largest positive unsigned int is approximately twice as large as the largest positive int, so you can get some flexibility there. Character types. Remember char, the type we can use to hold a signed character? I have a shocker for you. It's actually an integer. Change this. Deep down, char is just a small int, namely an integer that uses just a single byte of space, limiting its range to. Here, the C spec gets just a little bit funky. It assures us that a char is a single byte, i.e. size of char equals 1, but then in C11 goes out of its way to say a byte is composed of a contiguous sequence of bits, the number of which is implementation defined. Right, but in most modern CPU architectures, we're going to say that a byte is 8 bits long. That's what we're going to say. I'm saying it. We're saying it right now. We're going to say it, okay? So, but assuming, wait, what? Some of you might be used to the notion that a byte is 8 bits, right? I mean, that's what it is, right? And the answer is almost certainly. But C is an old language, and machines back in the day had, shall we say, a more relaxed opinion over how many bits were in a byte, and through the years, C has retained this flexibility. But assuming your bytes in C are 8 bits, like they are for virtually all machines in the world that you'll ever see, the range of a char is... So before I could tell you, it turns out that chars might be signed or unsigned depending on your compiler, unless you explicitly specify. In many cases, just having char is fine because you don't care about the sign of the data. But if you need signed or unsigned chars, you must be specific. Char A could be signed or unsigned. Signed char B, definitely signed. Unsigned char C, definitely unsigned. Okay, now finally we can figure out the range of numbers if we assume that a char is 8 bits and your system uses the virtually universal 2's complement representation for signed and unsigned. So assuming those constraints, we can finally figure out our ranges. Char type, signed char, minimum of -28, maximum 127. Unsigned char, minimum of 0, maximum of 255. And the range for char are implementation defined. Let me get this straight. Char is actually a number, so we can do math on it. Yep, just remember to keep things in the range of a char. What about those constant characters in single quotes like B? How does that have a numeric value? The spec is also hand wavy here since C isn't designed to run on a single type of underlying system. But let's assume for the moment that your character set is based on ASCII for at least the first 128 characters. In that case, the character constant will be converted to a char whose value is the same as the ASCII value of the character. That was a mouthful. Let's just have an example. This depends on your execution environment and the character set used. One of the most popular character sets today is Unicode, which is a superset of ASCII. So for your basic 0 to 9, A to Z, and punctuation, you'll most certainly get the ASCII values out of them. Okay, cool. More integer type. Short, long, 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 long. So far, we've just generally been using 2 integer types. Okay, we're going to skip through all that. I don't need these long, longity, long, long. Short is a 16-bit. Int is 32-bit. Long, long, long. So wait a second. Why does his int up there have negative? On my computer of 64-bit ints using 2's complement. Okay, so you have 64-bit ints. So unsigned long, long, long. Long, long. there is no long type. You can't just keep adding longs like that. Don't be silly. 2's complement finds man some funny about these numbers. Why does, for example, the sine char stop at 197? Remember, these are only the minimum required. Some number representations like sine and magnitude top off at plus or minus 127. Let's run the same table on my 64-bit to see what comes out. Min bytes, my bytes, 8. So int, long. That's a little more sensible, but we can see how my system has larger limits than the minimums in the specification. But what about, what is the size of my machines? Printf, %d, no, percent size of int in my machine. Percent long integer for size t, I believe, right? Size t. Let's go to terminal. Size t, man, size t. Size t, count of bytes. Type def used as a result is an unsigned integer type capable of storing values in the range size max. Okay, so that's the long. Okay, so, and then we want size of just the int, size of I. Size of I. Right? Okay, so then we recompile this. And then we go back to the terminal, quit out of that, and test it. Size of my machine is 4. So size it, so 4 bytes, so 32-bit. But okay, so long would be 8-bit or 8 bytes or 64-bit in my machine. Okay, cool, that makes sense. Okay, so there's a little bit of sensible, more floats, double and long double. Yeah, I don't think I'm gonna need those right now. How many decimal digits? The million-dollar question. How many significant decimal digits can I store in a given floating point? I'm not worried about long numbers right now. Constant numeric types. When you write down a constant number, like it has a type, but what type is it? Let's look at how C decides what type the constant is and how to force it to choose a specific type. Hexadecimal and octal. In addition to good old decimal like grandma used to bake, C also supports constants of different bases. Hexadecimal and octal. Okay, so I think we're gonna jump into those on the next stream. So we're looking at 5815 is right now. So we're gonna jump into those on the next stream. And for now, we're gonna jump into looking at this prelude Emacs Kickstarter template. So if we go to Emacs Prelude in our search here, DuckDuckGo, what does it say about it? So Prelude is an Emacs distribution that aims to enhance the Emacs experience. So if you were to look at my Emacs right now, my Emacs.d, my init, it's just a basic initialization, and then I'm using a config here, org file for config for, let's open everything. Just a few items in there. I kind of use it on my work machine as well. So I wanted to try out Prelude because there's a lot of cool keystrokes for Prelude that I wanted to look to. It doesn't run super fast on my work machine, but I'm sure it'll run pretty quick on my, this is my personal machine. So yeah, so we're gonna do it and then just run with it. So let me pop that out of there, and I'm just gonna resize the Prelude over there, and then we'll get the terminal back here. There, we'll get the terminal back there temporarily, so we can get the terminal back like that. Okay, so it's an improved UX that's still in line. It comes with a lot of cool Emacs features. So let's just go to the installation. It does some cool configuration. We'll go over that in a minute. Where is there dark mode? Dark? Where do I get dark mode? I wish there was dark mode. There's supposed to be dark mode. Profiles? Supposed to be, I thought there was supposed to be dark mode. Let me see if there's a dark mode in. Bum, bum. Yeah, dark mode right here. Add to Firefox. Okay. So now. Oh. Oh, that was cool. Oh, that was real cool. I like that. Okay, sweet. So now we have a dark mode while we're reading through this. Okay, so there's the personalization settings. So contributing. Let's get to installation. Frequently asked questions. Where's the menu here? Installation. Installation. Okay, obviously to use Prelude, you have to have Emacs installed. For fly spell, you should install a spell together with its dictionaries for the languages you wish. You also do well installing Git. We know we have that. The Silver Server, Rip Grip, Projectile has nice integrations with them, and they're much faster than grep. Your favorite lint tools for fly check. All of those tools are completely optional though. Okay, I'll install some of those. So let's install sudo apt install AG and ripgrep. Unable to locate package AG. Sudo apt search AG. Sudo apt install ripgrep. Install recommends. Install recommends. Install suggest. What is AG? The Silver Searcher? Sudo apt install AG. AG, the Silver Surfer. The Silver Surfer. Oh, or ripgrep. Yeah, I do have ripgrep. Okay. Or, I didn't know it was an or. Okay. So, all of these tools, your favorite. Installing Prelude. You can install by the command line with either curl, naturally git. The installer do the following: clone, git, check your Emacs version, back up any existing you might have, create additional folders if necessary. If you have it, it will be backed up. If you're using curl, do I have curl? Curl? No. I do have wget though. And I should have curl. So let me do curl. Sudo apt install curl. I should have curl. Curl's a... so I do have curl. Oh, duh. Okay, so let's copy this command here and curl it. And let's just... Oh my god. Let's install it. Okay, so we're installing Prelude. Compiling it is now installed and ready to use. Okay, so now we're gonna close Emacs. We're gonna close the client as well, PSE, the server as well, because that's the only way it's gonna install it. Grep Emacs, kill the server, 15544. Okay, so we've killed the server. Now we're going to start the Damian back up. And this time it should be installing all of that stuff for Prelude. So there it is. It's going crazy. We're going crazy, installing all the Prelude stuff. Wow, there's a lot of Prelude stuff. Okay. But I just want to program. So that's kind of why I like this, because it's a good starting point. It's not as heavyweight as It's not as heavyweight as would be Doom Emacs, and it's not as heavyweight as would be Space Emacs, so it gives you a good, sane starting place to begin with. Okay, so that's done. So now we could do Emacs client, I'm believing. Emacs client and the R. There it is. Oh, that happened. Why does that happen again? There's like a bug in Wayland where that happens. So now I have to kill Emacs again. There's 2 Emaxes? Okay. So Emacs, Damon. Okay, so now there we go. And this is the kind of a cool, look at that, Control C, Control, and then D, Control C, and then Control that for the prefix, and then I could search in GitHub or like search at DuckDuckGo. So if I do D here and I search DuckDuckGo, I could be like, I could say scan fs. Look at that, opens DuckDuckGo, searches for it. That's actually kind of cool. That's pretty cool. I like that. So okay, we got it installed now. So let's go back up to the table of contents. Installation, installing, pinning, enabling, updated, installing, trouble usage. There we go. Nothing fancy here, just start Emacs. Personally, I run it in Damien mode. Afterwards, I connect. Getting to know Prelude. So here's all the Prelude kind of thing. So let's open back up that C that I was working on, like the main one, right? The main.c. Okay, so company backend, company clang could not be initialized. Company found no clang executable. Oh. So I need to install clang for that to work then, huh? Okay. So let's go install clang in order for clang to work. Sudo apt install clang. Nope, that's not how you spell it. That's not how you spell it. I spelled it wrong. Spelled it wrong. Wrong speller over here, folks. Okay. Try again. Sudo apt install clang. Now I put in my super secret password. Seriously? Password I don't know. Let's install the suggested. Let's install the suggested. Yeah. So we're downloading everything now from the repositories. It's installing clang. Run sudo system ctl daemon reload to trigger the units. Okay, I triggered some units. Okay, so now if we kill this buffer and then we roll this buffer back, main.c, now the company is there. Now there is one that was cool. I think there is a Automatic indentation or cleaning up of your file. Where is that? Prelude mode. Indent region of selected or entire buffer. Okay. Fix the indentation and buffer and strip white space. So that's Control C. Does it have minor mode? It doesn't have the prelude mode here. So let's see if, okay, so if we do Control C, does it have, okay, they're called crux, okay. Clean up buffer, yeah, N. There we go. So it cleaned up the buffer. Nice. Indented it, cleaned up the white space. So it's probably, what is the C style? So let's describe the variable C style, C style variables. Values, no. Oops. Set C style. Because you could do set C style, C set style. What is it currently? K and R, right? Control C and okay. So K and R, yeah, K and R is the one I like. Okay, so that was kind of cool. You can duplicate the lines, you can move lines around. Wait, what is that? Where's the moving lines? Moving a line is up in the higher one. Move the current, yeah, move the current line up or down. So Control Shift, so I can move this line. Control meta up or down. That's kind of cool. Because that's not super easy. So that's the crux. That's all of the stuff that you get added through this crux thing. So I have this cheat sheet. So yeah, I'm going to continue to play with this. There's a cheat sheet. You can actually print it out. So let me see. I think there is getting to know prelude. Where is the cheat sheet? Key chords. I like the key. Okay, cheat sheet. Generate. You'll need to install a tech afterwards. You can do something like. But does it not have it in there? So if I open D, does it not have the does it not have the Yeah, it does have the PDF right here. Docs, prelude, there we go. There's the cheat sheet. So I could open this, Dirid open, Crux open with Crux open. There we go. Sweet. Look at that. I opened it in my viewer. And then I could print it. Print that. Preview. Okay. Print it. So that should be printing it now. Maybe not. Looks like it failed. Force quit. Okay, so let's do. So printing. Which one is actually alive right now? Printers. Which one connected? View print queue, nothing. Properties. Toner ink levels. Okay, so that one doesn't have it. What about this one? Properties. Okay, this one. So this is the one that's the actual printer. This one right here. This is the one. That's the one I want to set to default. So let's go back into printers. And let's set this one as the default. Yep. Okay, so that's the default. So now if I print, it should print it. So it's printing it upstairs. So it's printing it, and then I'll have the cheat sheet available, and then we'll be able to use that. So let us go ahead and end the stream for tonight. If there are any questions, I'll stick around for just a few more seconds. If anybody has any questions, please post them in the chat, and I'll answer those, and then we can go ahead and close the stream otherwise. I need to turn off this. Boom, 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 boom. Okay. Sounds like there's not any questions. So with that, I will add another scene. Let's go to studio mode. Add another scene. We're going to call this large scene. Large. And it's just going to be a camera, video capture device, Brio 101. Okay. Transition here. No. Main. Large. Let me delete that. One moment here. I'm trying to get my camera to go large so we can transition back. Oh no. Okay. Copy. Okay. Okay, so that's just a big view of me with the new camera. I did get a new camera. It does look a little bit better. This is just a black screen view, but I want to thank everybody for joining. Again, if you like this, give me some ideas on stuff to continue. I know the learning to see is going kind of slow right now, but we're going to eventually get to the point where we'll be actually producing something on our daily streams. I think for some of the weekend streams, maybe we'll jump back to another language which I'm more of an expert at, and we can build something there. Let's get for that push for 100 subscribers. I thank you guys all for joining. Until next time, this is Keenan Can Do. I'll talk to you later.